But first, let's tackle the volume question. So I want to start with the example that's up here on the board. I've got a kind of a crudely drawn here square pyramid. So we're to think of this as a pyramid whose base is this square that I've sketched here, which is 5 by 5, and whose height is evidently 6. So the height of this pyramid, as measured from the base to the tip of the pyramid perpendicularly, is 6 units. So of course my question is, what's the volume of this pyramid? So how in the world are we going to answer this question? Now you could rewind the tape to solid geometry and just dust off a formula from solid geometry that tells you how to find the volume of a pyramid. The problem with that formula is it's not very extensible in the sense that it can tell us how to find the volume of a square pyramid, but it can't tell us how to find the volume of other things that have square cross-sections, but which might not be exactly pyramids. Things like the solids that are on the front of your page today. They have square cross-sections, but they don't have those straight sides. They have curvy sides that might be described by the graph of some function. Or equivalently, like the examples that are on the back side of the page today, so groups C and D, are looking at solids that have circular cross-sections instead of square cross-sections, but which aren't exactly cones, right? They don't have a straight path from the base of the cone up to the apex of the cone. So the reason that these are calculus problems is that we're going to build up the volume of these solids using the areas of cross-sectional slices. So the same kind of thing that we did for the building up the area between curves by finding the areas of tiny little rectangular slices. We're going to find the volume of these solids by finding the volumes of tiny little cross-sectional slices and adding them up using an integral. And this method is going to allow us to find these volumes no matter whether we're looking at a nice pyramid or cone that has straight sides or whether we have something with curvy sides, as all of your groups have to work on in the second half of today. So as you were looking at the videos and reading the material on this phase of the section, what was it that came up? What were your responses to what you read and what you watched that pertained to finding the volumes of regular solids using integration? On the diagram at the top, I've sketched in a red line that sort of gives a xy coordinate equation for the top face of this pyramid. And if that face is a straight line, can you tell me how to find an equation for that straight line based on the information that we have? Any ideas? Let me get you started for a second. We know that one of the points on this line is going to be at the origin. Y equals x. Perhaps. That certainly goes to the origin. But the issue is, in order to determine an equation for a line, we really need 2 points. And Euclidean geometry tells us that in between any 2 points in Euclidean space, like the plane or 3 dimensions, there is one and only one straight line that passes through that pair of points. So let's find where one of those second points is located. And I'm going to label the point here that's on the base of the pyramid. So what can we say about the coordinates of this point here, which is at the base of the pyramid? Which coordinate do we know right off the bat?
Yes.
Yeah, we know the x-coordinate is 6, because that's where we've declared the base of this pyramid to be. So now all we need to do is figure out what the height is. In other words, I need to measure that distance from the x-axis up to that point, and that's going to be my y-coordinate. And what is that distance going to be if this pyramid is indeed centered on the x-axis? My drawing is a little bit wonky, but we'll imagine it's centered on the x-axis. 2.5, right? It's half of the total height of that base. So let's call the y-coordinate at that point 5/2. So we have a line here which passes through the origin of the xy plane and also passes through the point 6, 5/2. So we know the y-intercept of this equation is going to be 0. But what's the slope? If I have a line that passes through the points 0, 0, and the point 6 comma 5 halves.
2.5 over 6.
2.5 over 6. All right, y2 minus y1, 5 halves minus 0, divided by x2 minus x1, 6 minus 0. 5 halves over 6, otherwise known as 5/12. So an equation for this top side of the pyramid is y equals 5/12 x. That's not a step that you'll always have to do. This is my sneaky way of getting us to talk about slope again. But at least, at least in the questions that you'll be doing in your groups today, that part is already done for you, that you have an equation which describes for you the top side of your pyramid or the top extent of your cone if you're working on the circular cross-section questions. But it's important because it now tells us how the size of these slices is varying as x changes. As we choose a different slice of this pyramid, how are we getting a different area for that slice? So now let's go back and do the same thing that we did with our area example and pick an arbitrary x here in the middle. We could start by picking a specific value of x, but since I want to get you into your groups and working on this sooner rather than later, let's do this a little bit more quickly here. So what I'll have is the following slice going on. Try to make this as accurate as possible, but this is not going to be the greatest picture in the world. So I get some slice there in the middle at the location x. And the height of that slice is what? If I'm taking a slice at x, then what is the height? Not the height, but rather half the height here of that slice. From the x-axis up to the top of that slice is how much distance?
Over 2 minus y. You don't know the height yet, but you know how tall it is.
Well, we know how tall it is, right? We know that the very top of this slice is on the graph y equals 5/12x. So there's a top. And the bottom of this little line segment that I've drawn here is where? I should probably do this a little more smartly. So we've been a little bit, okay, I'm going to do this a little different. Let's extend this all the way down to the bottom. Where would this point be on the bottom? Y equals what? Negative 5/12x. It's the same line on the top. It's just been reflected down to what would be the fourth quadrant in the xy plane. Y equals minus 5/12x. So we can think of this as being like an area between curves problem now, because the height of my square, clear out some space here. How am I going to find what that height is? Declutter this a little bit. If the top of my line segment is on y equals 5/12x and the bottom is at y equals negative 5/12x, then what is this height, which is what we called s before? Yeah.
2 5/12x.
Right, twice 5/12x, because it's the top function minus the bottom function, 5/12x minus negative 5/12x, which gives us twice 5/12x. And twice 5/12 is just 5/6. There we go. So one side of this square cross-section measures 5/6 x units, if you like. And now that we know how long one of the sides is, we can find the area of this particular slice. It's just that side squared. So 5/6 x, the quantity squared. If you like, that's 25 over 36 x squared. So that expression, 25/36 x squared, gives me the area of this green cross-sectional square that's sketched in here. So far, so good? But the question's not asking us for an area. The question is asking us for a volume. And so what we really want to do is we want to get to that volume by adding up little teeny bits of volume using an integral. So we need to give this square, this cross-section, we need to give it a little bit of thickness. And the little bit of thickness that we give it comes from the x-axis. And again, it's going to be one of these infinitesimal quantities that we're going to call dx. So in other words, I'm kind of setting up a situation here where I've got, I'll try and draw this as sensibly as I can here. So I've got this slice that has a little tiny bit of thickness that we call dx. And therefore, this slice is now going to have some teeny tiny bit of volume that we're going to call dv. So how do I find the volume of this slice? Since now I know its area and I know its thickness. How do I get the volume of a slice if I know the area and the thickness? Just multiply them together. The area of the slice times the thickness. Our thickness is what we call dx. And our area is this expression that we had from down below, 25 over 36, x squared. And this is how much volume we have in this one teeny tiny little slice. Now, how do we go from that volume to the entire volume of this pyramid? What do we do with infinitesimal elements to turn them into tangible quantities? That's what makes it a calculus problem. Integrate it. So I'm going to integrate dv. And my limits of integration here are limits on x. What are they? 0 to 6. X equals 0 over here at the left endpoint, at the apex of the pyramid. X equals 6 at the right endpoint gives us the base of the pyramid. So now I know what to do. Again, in all of these kinds of problems, setup is everything. Because from here, the actual calculus, finding this antiderivative and plugging in the limits and subtracting, is fairly straightforward. So it's the setup that consumes most of your time. Taking a cross-sectional slice, finding out how its area depends on x, that's the fun part. And then giving that slice an infinitesimal bit of thickness, dx, and adding them up using an integral. Give me an antiderivative for 25 over 36 x squared. Sure. Increase the exponent, and then divide by the new exponent, which is 3. Okay. Gives me 25 over 108. Evaluate that from 0 to 6. At 6, we end up with 25 times 6 cubed. Anyone know 6 cubed off the top of their head? 216. Excellent. Times 216. But then at 0, this just disappears, and we get this fraction. Anyone want to reduce that for me real quick, because I'm feeling less than inspired? $216 over 108 has to reduce. Hey, that's a nice number. Cool. So the volume of this pyramid is 50 cubic units. Questions on this volume example before we talk for a few minutes about average value and then get into your groups?